My name is Sherin Mathews, and I'm here to present my work on federated learning. So this is relevantly a new area of research that I'm focused on looking at how this could be applied for all applications related to businesses and even corporate areas. Let me advance the slide. Okay. Just a little bit of background about myself. So I'm currently a principal AI research scientist at US Bank, and my background has been in the area of computer vision, and I have previously worked in the domain of applying or developing deep learning algorithms for cybersecurity problems like ransomware, steganography, deepfakes, all those threats. So yeah, that's about me. And if ever you have any interest or any kind of talks that you want to discuss about security issues, feel free to reach out to me on LinkedIn or Twitter, whichever works convenient for you guys. So this is the outline of my talk. I would first like to introduce the topic of federated learning and why is it relevant at this stage. Next, we'll focus on the design aspect. Like if you're looking to design a federated learning system, what are the design constraints that you need? Like what is the distribution that is needed? What kind of scale that you need? All those aspects. And then I think finally, and the most importantly, I will try to focus on the open areas of challenges. What are the security challenges that are currently there in this area, and then focusing on the training challenges, and kind of finally talk about the applications and conclude the session. So importance of data for ML. I think data is, the lifeline for building any kind of AI model. With that being said, it is of significant priority for all businesses, especially in financial services. Now, with the advancement of technology, companies try to leverage other kind of data like tracking customer activity, looking at other sources of data that can be used to append to the existing data form and then contextualize that data and draw some kind of insights. Now, that's where it kind of brings to the point like, are we concerned about the privacy and the security of the person or the client that we are focused at? And that kind of focuses on this topic of federated learning. Now, several factors have led to the global consensus for people focusing into the part of data privacy. As traditional machine learning algorithms have been exposing a lot of their drawbacks, finding new and even secure ways to collect data and even learn from their data becomes crucial. And thereby, this opens research avenues for us to build personalized machine learning or deep learning models without violating any kind of user privacy or having constraints there. In addition to your data privacy issue, you have data isolated islands. One might ask, what is it, right? So when you're talking about traditional machine learning algorithm, you have your data collection, you have your pre-processing, you have your training. All this requires all your data to be at one point wherein you can perform uniform cleaning, pre-processing, and training. What if you have data stored or maintained at different areas, something like isolated islands? Now, in order to solve this problem, I think one aspect here is making use of federated learning. What federated learning brings into play is it actually brings the model, which might be your central global model, to your client system. So to give an example, I can kind of give you a very high-level idea of what's been mentioned in the academic research. It is considered to be a machine learning paradigm wherein you can have multiple entities. They can collaborate into solving a machine learning problem. What does it mean is I might have a central server, might be my own system. I might have a number of clients which might be able to use or build their own machine learning models at their end, keeping the data private to them. And I only transfer the model updates to my centralized server. Now, this ensures my data is being private. The person who is at the central system has no access whatsoever to the client's data. So each of those clients' data is actually stored locally, and it's in a decentralized format. And you are not kind of exchanging or transferring any information there. The thing that you're doing here is only transferring the model updates from each of your clients to your centralized server, which might be used for updating your model or improving your model per se. I think the slide is a bit skewed, but I think just ignore that, sorry about that. But this is like an overview of what a federated learning system looks like. Now, as I said, it's a distributed machine learning architecture, which essentially will try to solve the problem that you have with a centralized system. You might want to bring your data to your centralized server. This will help you solve that problem. You are able to have your data at your system, at each of your systems, IoT devices, and you're only sending your updates to your centralized model. So essentially, what you're doing here is you're bringing your model to your data rather than taking your data to your model. And that helps you to generate more robust models without sharing data, thereby leading us to have extremely privacy-preserved solutions with higher security. Again, if you still ask me why, if you have seen threats like ransomware where people have been able to download some kind of file and completely encrypt your system and not gain back access to your system, having federated learning systems helps you to be resilient against attacks like that. So I think that kind of improvises and helps us to understand why federated learning system is needed across the system. Now, it can be done across devices and it can be done across organizations. So say you have an IoT system from where you are trying to get the user data or the client data. You can have a model which is being developed at each of your IoT device, and you can have a centralized server which accumulates the updates and sends the model back. Otherwise, you can have across organizations, say I am a central system where I am trying to get data from all my clients, and I can have each of my individual clients run their machine learning model on their private data, and I only get the update. I am not having access to that data. So that thereby helps me to preserve or at least have privacy for each of my clients. Now that we have at least a good understanding, or at least a one-on-one understanding on what this concept of federated learning is, I think let's move on to what is needed to build a system like that. I think the four main pillars here are, when you're trying to build a federated learning system, these are the four main architectures. One, how is your data distributed? How do you want your data to be distributed vertically, horizontally? I'll speak about that in the next slide, but just giving you a high-level idea of these are the four main aspects that I need to keep in mind when I'm developing a system like federated learning system. Now, next is the scale of federation. Do you have a small sample size? Do you have a lot of organizations taking your data? Depending on that, you might want to use a cross-silo or a cross-device-based data. What are the privacy mechanisms? I think that's the cream here. What kind of encryption mechanisms are you using? Are you using homomorphic encryption? Are you using differential privacy or SMC? Whatever kind of privacy mechanisms kind of fit in your whole play. And last one, I think I'll just enumerate a few open source frameworks. There are a few open source frameworks which are currently available for both research and development purposes, which allows us to develop federated learning solutions at scale. So I will enumerate a few for folks who are interested there. Talking about data distribution, I think the three main categories here are vertical federated learning, horizontal federated learning, and federated transfer learning. I can give you an example that makes it easier. So suppose you are working with an Excel file. I have a vertical federated learning system means I would have the same feature space for one user, and I'm trying to add another feature for a new user. What does that mean? Suppose I'm trying to improve my marketing scheme from a bank side. Say I have a credit card decision. I want to have a better model from my side. I will try to tie up with an online site where I'm trying to get a data from the site, understanding what kind of things does the user usually buy. Using that acquired feature or in a privacy-preserving way, using federated learning, helps me to build a meta model in a way that I can give some kind of point allocation system to my user. And on the other hand, the online shopping site, which might be using my data with a privacy-preserving way, can give some kind of point system. So essentially, what this vertical federated learning system does is, you might have a feature or a tabular data. You're basically adding more features to your entire data. Whereas if you're looking at horizontal federated learning, you're basically adding more rows to your data. What does that mean? That means you're adding more clients to your data. So you might not have better feature space, but you might have better, I would say, distribution of the data. Next one is the last one, the federated transfer learning. I know folks must be aware of transfer learning. Transfer learning is a technique where your model is assumed or well known to be doing something at a particular task, a pre-trained algorithm. And you're trying to modify that for a slightly similar task. For example, I have built a model which can look at my user's movie, I guess, the things he usually watches. And I'm trying to build a movie recommendation system. If I am trying to use a model for a slightly similar base task using a pre-trained algorithm, I can make use of a transfer technology in federated learning. So that is what is called as federated transfer learning. So these are, I think, the three main pillars. Depending on what kind of data you're dealing with, you might want to use any one of those approaches. So this is an example of this. Let me see if the clicker works. Yeah, here. OK, good. So the example here of federated learning, vertical federated learning. So as I said, you might have, say, an online site where you have data for person 1. I have a hard time reading, but yes, articles read, articles written, all those features. So for my person A, person B, person C. Now I have another online website where I have the information of the same person, but I have title, category, author. So basically, I am adding more features, combining them by a join function, and I'm adding more features, thereby enhancing my, I would say, training set. Whereas in horizontal data, you're just adding A, B, C. Basically, you're having more data as per your client. So this is a good example explaining the difference between a horizontal federated learning and a vertical federated learning system. Next, scale of federation. This kind of comes into play once you have decided post your data distribution. So once you have decided you're going with a horizontal learning system or a vertical learning system, you might want to interpret whether you want to do a cross-device or a cross-silo. This research is extensive. This is just one slide showing the whole research. But if you have a large number of participating devices, you might be better off using cross-device systems. However, if you have, I think you have more rounds and you are having less number of devices, then you might use the cross-silo devices. But I'm just giving you an overview here, and as I said, this is a very extensive research. Just kind of give you a nutshell idea of what it, like the very 101 of it. Next one, I think the most important part, the whole point of using federated learning is to ensure that you are having the data in a very privacy secure way. What do you use for that? There are two main functions or two main, I would say, categories for developing a secure privacy-based system. One is a differential privacy system, and one is a cryptographic method. Now, what does it mean? Differential privacy system is something like you add a certain amount of noise to your update. When you're building a model, you're trying to add certain amount of noise. You inject some kind of noise to your update, and thereby kind of not allowing your global server to understand what the model, where the data is coming from. Now, as you understand, when I'm adding some kind of noise to my model, there might be some, I guess, accuracy issues that might get introduced. Now, what does that mean? That my accuracy will go down. So I think that's one of the big drawbacks with differential privacy systems. Whenever you have systems like these, they might tend to be less accurate as compared to the other methods that I might enumerate. Next one is cryptographic methods. For folks who are in security, will know the two main categories in cryptographic methods are SMC and homomorphic encryption. Now, both these methods, what does it do? The advantage of it, there's no noise added, so accuracy will still remain intact. But what exactly happens in this whole category is you will try to encrypt the data before sending the data, and then once the client is at the other end, he will do some kind of decryption to get the data back. What does that introduce? It will introduce some kind of computational overhead, and that's the drawback you might have to live with. So overall, depending on your use case, what works best for you, you might be better off choosing one of these two. Okay, lastly, the open source framework. I think these are the most advanced ones. PySoft, Fed, TensorFlow, Federated. PySoft is written in Python. It's built on top of PyTorch. And it basically allows some kind of virtual hook or a WebSocket port that you can use to develop or even develop and even use existing federated learning solutions. Next, it's a Fate model. It's basically, it provides more of a, I would say, a web user API-based integration. You can integrate that with Kubernetes and use that for developing any kind of existing federated learning systems. Last one, TensorFlow Federated, as the name indicates. It allows more of integration with Google's Kubernetes platform and helps you to develop solutions or even develop solutions using federated learning systems. Now, these three are the most commonly used, I would say, open source platforms by researchers if you are looking to apply existing federated learning architecture for your use case. There are a few more, but I think these are the ones I would like to recommend if folks are trying to look into this aspect. Okay, so I think I'm good on time, but let me know if I go over. But I think last one, the security challenges and the training challenges. So these are, I would say, the open areas of research that still has a lot of improvements to be done. And if folks are interested in terms of research, this is a great area to look into the aspect. Now, looking at security challenges. The whole point of federated learning is to ensure that the data is secure and private. Now, despite the options being offered by federated learning, there is always attack mechanisms happening. Now, what kind of attack, or folks who have heard of adversarial machine learning, what does it mean? Whenever an adversary tries to attack a system, it can do three things. One, it can try to attack a system saying like multiple pings, try to see where my model fails, one way. Second way, I can give in some kind of backdoor data, backdoor functionality, which can affect my client model and cause it to fail. The third way is try to inject some kind of poison data to affect your client. So I think these three are the major pillars of security challenges, and all of them fall in the category of targeted attack or untargeted attack. Now, when you look at the broad pillar of targeted attack, what you're essentially trying to do is you're trying to make your model have some mistake or have influence the prediction on a certain specific task. Whereas if you're looking at an untargeted attack, you are essentially targeting your global models. So consider you have your global model up there, you have all your client models down here. If I'm only concerned about affecting my entire accuracy of the global model, I would kind of essentially go for a targeted based attack. If I'm looking at only affecting one client or one of those clients' model, I might look in for an untargeted attack. Now, inference attack is one of them, wherein what it does is an attacker can infer sensitive information to which it has no previous granted access. How would you do that? You can query the model several times and see, oh, this category, it fails. This category, it does not pass, right? So you are trying to make use of some kind of prevailing existing information to see whether you can make that client model fail. So that's inference attacks. Now, how do you mitigate it? The first solution here is differential privacy. As I said, differential privacy is wherein you add some kind of noise to obscure your sensitive data, and once you do that, you are rendering your inference attack ineffective. Next one is calibrated domain-specific augmentation. That very much depends on the problem that you're solving. So if you're doing an image recognition kind of task, you might be using frameworks like SMOTE, whatever kind of augmentation that might work better for that particular use case. I think the last one, trusted executive environment and secure computation. Again, you can essentially run your entire model in a TEE, trusted execution environment, and thereby prevent any kind of attacker. But as I said, there are overloads or drawbacks for each. You might be better off choosing what is better for your use case. Now, with that being said, these are all very, very early stage research. Still, we are at a very early stage to have more research in this area and pivotal to shape this in the future. Next one is the model poisoning attack. So model poisoning attack is basically you try to add some kind of a backdoor functionality, and you are trying to attack one of my clients. So I have my global model, I have one of my clients. I am trying to poison my local model rather, instead of the data. Now, how does that do is you will modify the functionality for one of those clients. You train the model on that data. You are affecting the model's parameters, essentially shifting the boundary, introducing error, thereby reducing accuracy. So that's what a model poisoning attack does. Now, how do you mitigate or defend against these attacks? Say I am at the global server, and I feel that I want to assess whether any of my clients have been poisoned. So what I can do is I can have a function or an error function which rejects a model based on the error rate. Say I have a threshold of certain percentage. If my threshold percentage is bigger than that, I would be essentially rejecting that model based on that function. Next, I can have rejection based on the loss function. As we all know, machine learning algorithms have this optimization function that we essentially work on. You can have a loss function being added, which can reject ultimately your client model based on a higher loss rate. Next one, you can have outlier detection or anomaly detection based algorithms if you feel, if you want to add to your current existing design framework. And then participant level differential privacy, depending on each of those clients, you might want to add, I would say, noise to each of your model. Last one, data poisoning attack. Data poisoning attack is basically you are poisoning the data, simple, and you are trying to compromise the accuracy of the global model based on just that. There are two main subcategories here. Here what happens is the first one, label flipping. As the name indicates, you are flipping the label of that client to make sure that, to basically affect that model's accuracy and thereby decreasing the whole model's functionality. Next one is the backdoor poisoning. So in terms of backdoor poisoning attacks, instead of introducing a backdoor data, you are trying to tweak your local model's data, and then once that is done, essentially it will tweak your features, and then they get transferred to your global model. How do you, I would say, detect this one? Use clustering algorithms. So in clustering, what do you see? You have your feature space where you can see how your models, I guess, your features are lying, right? You can make use of dimensional reduction algorithm that's being mentioned. So if you have a percentage as to which you are okay with letting that much amount of noise being happening, using clustering algorithms can help you segregate between a poisoned model versus, I would say, a distribution change-based model. So that's one technique. And as I said, these are all still something work in progress, and there is a lot more to do in this area. I think next one is looking at training challenges. Federated learning as such is at a very early stage of research, and the training challenges are still along with it. So we don't have much of training challenges that has been enumerated here, but definitely I would like to talk about a few here. The curse of dimensionality. Now what happens here is you might have an adversary that might be able to trying to make some kind of very minute changes in your high dimensional environment without being detected. Now, what you can do here is you can not share that information or share only the model prediction in a black box manner, but that might not be the ultimate solution for solving this kind of issue. But there is, as I said, these are all open areas of research. If folks are interested to further this research, this is something that still requires active area of research. Next one is optimization for defense mechanisms. Now, if you recall the previous slides, I had multiple defense strategies. Now, when you have multiple defense strategies, when you try to make use of a couple of them, you are adding computational cost. Now, how do you optimize for your whole framework where you are having disparate defense mechanisms and they have different effectiveness against these kind of attacks? What works best for you? What works best for your use case? That's what we are trying to do in using optimization systems. And a solution here is making use of game theory efforts. Next, I think last two, the decentralized federated learning system. Now, this can be applied in a way that whenever you talk about federated learning system, the model updates that are currently being used are only presented in a homogeneous environment. Now, when you talk about heterogeneous environment, there is no existing architecture, at least I am not aware of it, which is currently in place. So that's another open area of research that is still open for research here. Lastly, I think applications, wide. You can use in finance, you can use in NLP-based use cases, you can use in machine learning, image processing, whatever use case you're working on. So for example, you're talking about portfolio management system. You with the use of federated learning, what you can do here is you can get data from third party, like robo-advisors, portfolio management system. Get the data in a very secure way and apply to get better models for your whole system. Next, loan risk assessment or even risk assessment, both are kind of similar. Say I have my FICO score coming in from somewhere. How do I get that data in a highly secure manner without sharing any kind of user private information? I can make use of federated learning architecture. So that's where I think federated learning architecture has place. Lastly, you can integrate that with open banking system, and also it can be used for multiple domains like money laundering. So this is very, very high level of specifically in banking where it could be used. But that being said, it can be applied for numerous areas of research, be it in image processing, NLP, and other domains. I think this concludes my slide. I won't keep you away from lunch, but concluding the slide here. So as I said, this is a very, very early stage of research, and it's a new paradigm in which what we are essentially trying to do is we are trying to build a model where we can have a shared model while preserving the user privacy. Now, it helps you to have a very high quality shared model with a central server with decentralized data. And in my whole talk, I try to enumerate what are the design constraints, what are the things that you need to enumerate while building a system like this, and what are the challenges that are currently existing, be it in the form of a training system or a security system. Now, I think I just wanted to give a very high-level idea of what are the current frameworks, and yeah, I have outlined a few open problems, and I hope this helps promote some kind of research here. So that concludes my talk, and I'm happy to answer any questions. Yep.
Thank you, Sherin. One over here.
Hi, thanks for the great presentation. So has been like a shift towards, in the last couple of years, from model-centric machine learning to data-centric machine learning. Mm-hmm. And now with all these techniques of federated learning, differential privacy, so you don't necessarily have direct access to the data.
Correct.
So can you talk a little bit about the limitations that this imposes? For example, as you have less visibility on what the models are being trained on, you cannot do maybe you cannot do sufficient feature engineering, you cannot do data cleaning. So what kind of limits does this impose on the models and the performance that you're going to get?
That's true. I mean, you can look at it from different aspects. So the drawbacks that you see from a centralized system is you can have better feature engineering, you can fine-tune your model, improve that there. But you can essentially do that at your client level. You can pass on those updates. You can have better feature engineering. I mean, you essentially have your global model, which are you essentially passing to all of your clients. So if you can somehow pass those techniques for, I mean, having a deployment scheme where you're doing that at every stage, that might solve that problem. Yeah.
You kind of have to educate your clients
Yes.
as of the process to get you the data to train the models on their servers so you can get the weights.
So I think that's essentially one thing that you need to work on. And yeah, that brings about additional, that they should be aware of the techniques that works best for them. So it gives them that liberty as well.
Just have a quick question. I know that at least in my line of work, there is something called redaction, when you can just remove or kind of mask the important or sensitive data from text or speech directly. And I think in a couple of your slides in the training challenges or security challenges that can be used, can you just say, like, explain, have you thought about that and where does it fit?
So you mean how can you mask the data? Like what exactly?
Yes, so in the framework, the federated learning framework you explained, where does it fit?
Right, so I think so federated learning as a system is wherein you have each of your clients. You might have your features at each system. You are not sharing the features in any way. You are just sharing the model update. So that first thing is ensuring the privacy of your user. If you want to ensure, I think, additional encryption, you can have something like redaction or encrypting each of your features. That might help you to get essential added privacy. So that's something that you can do at your client level or also at your global model level.
And do you think if we do that redaction, does it remove the need for federated learning at some point? At least at some applications when that sensitive data is not very important feature.
Depending on what you consider as sensitive, right? So that also makes a difference. So say I have client-based data which I don't want to hide the SSN or something like that, but there might be other features which my client might not be comfortable sharing. So for those use cases, you might be better off using encryption algorithms or even systems like federated learning.
Thank you.
Sure. Hey.
Great talk. So I have two basic questions. You have to start somewhere, right? In terms of bootstrapping the federated learning, what are your thoughts? Second question, how do you benchmark the performance? If
That's
the,
very good
the
question.
data is sensitive, is there like a global data set everybody can share or contribute to? And also related to that, this feedback loop seems to be more challenging. So how do you version? Like, how does a client decide when to take an updated model?
Okay, two questions here. So first thing, when you mentioned about having a benchmark, I think that's still an open source, that's open challenge here. We don't have a benchmark even for homogeneous system where we can say, hey, this is my model performing 98% accurate and I'm good with it. Developing that benchmark is pretty important, be it in any kind of domain, like be it in NLP or image processing problem. So that's something that's still missing and it's still an open area of research. That's one. Next thing, I think in terms of feedback or if you see that one of your client models is not performing to the level it is supposed to be, you can make use of those defense mechanisms to say cluster and see my model is not performing efficiently. I can discard that model or not use that model for this update. But having that feedback loop is definitely missing, but that's where it is on that aspect, yeah. Follow.
Yeah, thank you for your answer. How about bootstrapping? Where do you start?
Like Ensemble, yes. So you can do that. Say for example, I'm just giving you an example. Say here you have multiple clients and you can cluster the model updates from each of your multiple clients and you can do that, like see whether they have a similar kind of data. And you can use those model updates to see whether you can look at the distribution of training data from each of your clusters and thereby group the behavior together. You can do that. I mean, that's something that is possible right now. Yeah.
Okay, great. Wonderful presentation, Sherin. Thank you so much.